In the past few lectures, we've talked about how lots of variables are approximately normally distributed, but how no variables are exactly perfectly normally distributed. So you might be wondering, how normal is normal enough? How do we tell if a variable is distributed close enough to normal that we can use a normal distribution and the tools for evaluating that distribution? And in what cases is the normal approximation unacceptable? We're going to look at two ways of visually checking whether it makes sense to treat our data as normal: the histogram and the normal probability plot. And for your reference, the normal probability plot is also known as the quantile-quantile plot. So you know how a histogram works. In this way of using a histogram to evaluate the normal approximation, we take the histogram and we overlay it with the best fit normal distribution. That is to say, if this distribution were distributed normally, what would that normal distribution look like? And then when we've overlaid this normal curve, we can look at how well the histogram data fits within that curve. Does it seem to fit pretty well, or are there lots of departures from sort of this ideal normal shape? So here we can see that there is some evidence that this data is sort of normally distributed. It's got one mode, the bulk of the data is toward the middle, and then it trails off more or less at the same rate to either side of the mean. And the data seems to be pretty well contained underneath the bulk of this normal curve. To the right of that is this normal probability or quantile-quantile plot. In the normal probability plot, the y-axis has the values of the data. So in this case, all of our observations of male height in inches. This is the y-axis here is the same as the x-axis in the histogram, just male heights in inches. And then the x-axis of the normal probability plot is something called theoretical quantiles. The mathematical definition of theoretical quantiles is complicated, and it's sort of beyond the scope of this class right now. But sort of suffice it to say that theoretical quantiles are just a way of slicing up different parts of the distribution of data. The important thing to know is that there's a straight line in a normal probability plot that goes from the lower left-hand corner up to the upper right-hand, and the closer the data points are to that theoretical normal distribution line, the more normal the data are. So you can see here that the plots of this data about male heights, the data is pretty close to that line. And the more linear, the more straight, the more tightly the data is clustered around that line, the more confident we are that we can treat this data as normal. So just to reiterate, in a normal probability plot, the data points are plotted on the y-axis and theoretical quantiles are on the x-axis. And what we're looking for is a linear relationship in the plot to show us that the data follow a nearly normal distribution. And finally, creating these plots is complicated if you were to try to do it by hand, so we use statistical software like R to create normal probability plots. So let's see if we can apply these graphical tools for evaluating the normality of data. Here we're looking at a distribution of heights, just like we were looking at before, except for in this case we're looking at the distribution of heights for NBA players in the 2008-2009 season. So take a minute and look at these plots and answer for yourself whether these data seem to follow a normal distribution or whether they are not normally distributed. Okay, let's take a look at this histogram first to try to evaluate how normally distributed these data are. We can see a sharp drop-off in this histogram at right around 84 inches or 7 feet. So the data sort of to the left side of the mean looks like it's stacking up nice and normally like we'd expect a height distribution to, but then when we get out to about the 7-foot mark, there's a sharp drop-off in the data. So this data is left skewed. And then when we take a look at the normal probability plot to the right, we can see that the data don't exactly follow this nice linear straight line. We can see it's a little bit of a curve down toward the lower left-hand corner of the plot, then curves back above that line for a bit, and then toward the upper right dips down below the line again. So we don't have that nice linear relationship that we're looking at. We're seeing quite a bit of divergence away from this line that we would like to see. If this data was normally distributed, we would see just a really tight linear relationship. So we know that we want to see a very close linear relationship in the normal probability plot if the data are in fact distributed nearly normally. But let's look at a couple of other shapes that we might see in the normal probability plot and what that would tell us about our data. So if the data is right skewed, we would expect to see this sort of swoosh, this U shape, bending around the ideal straight line. If the data are left skewed, we would expect to see this sort of inverted U shape where the points bend down and to the right of this normal line. If the data are not spread out as far as we would expect them to be in a normal distribution, so if the data has short tails, then we would expect to see this sort of S-shaped curve if the data are narrower than they would be in a normal distribution. Whereas if the data are dispersed wider than a normal distribution, if the data has long tails, then we would expect for these points to start below the line, then follow the line for a little bit, and then sort of arc above it. So that's just been a quick introduction to some of the graphical ways that we can tell if our data are normally distributed or not. Thank you for tuning in, and I will see you next time.